for part 2 of Notes 19, let's look at how we can use SAS to find this estimated model that gives us the best line that we can fit for a data set. All right, so here is the generic code. We're going to use a procedure called procreg, so the reg procedure, short for regression. Just like any other procedure, we'll put data equals the dataset name. We're going to have a line that says model. You may remember this from when we did ANOVA. We will have our response variable, an equals sign, and then our explanatory variable. And then if you want, you can have a line that says plot and response variable times explanatory variable. This will give us a graph of our data as well with our line on it, and then run. All right, and so we're going to do this for the burgers data set. And so I'll go to SAS on demand. You can see here's my 19-burgers. And hopefully you're getting in the habit of copying this and pasting it into a new program so that it doesn't give you any errors. And let me add procreg data equals burgers. Model, my response variable is calories because that's what I'm trying to predict. I'm going to say equals fat because that's my explanatory. And then I'll put calories times fat here and run. And let me run this and we'll see what happens. And you should get quite a bit of output here. This will actually look similar to what you saw when you did an ANOVA test. But what we're interested in is this box right here, the one that says parameter estimates. And down here are some graphs and things. And then here's that extra graph that we asked for. But I'm going to focus on this box. And you should have something that looks like this in the notes. But missing the parameter estimate part. So if I go back to the notes, remember that we said that the best line for the burger data had an intercept of 160 and a slope of 11.95. Well, if I go here and I do a little bit of rounding, sorry, that was 166 for the intercept. Here is 166 if I round to the nearest whole number, and here is 11.95. So it looks like this first row is my y-intercept. The second row is my slope. Now it says fat because that's the explanatory variable that I'm multiplying my slope by. So right here you can see that it's b1 times x times my explanatory variable. And so I could fill in these two boxes with what I had there. So what we're going to do is we're going to look at what those two numbers mean. All right. So we said that the y-intercept is 165.8405 and the slope is 11.95465. So again, it's this number for our estimated y-intercept and this number for our estimated slope. So how are we going to use those though? All right, well, one thing that we could do is we can use them to write out our estimated equation, our estimated line. All right, so if I'm trying to predict the number of calories, this is my equation to do it. I'm going to take 165.8405 plus 11.95465 times my explanatory variable. So in this equation, y hat is the predicted calories, and x is the number of grams of fat. And that gives me an equation that I can use to make predictions. So let's say I want to estimate the population mean calorie content for burgers that have 28 grams of fat. Well, at this point, all I need to do is take this 28, put it into my equation where it says x, because this represents the grams of fat, and whatever number I get when I calculate this right-hand side, that's my prediction for the population mean calorie content. So for this example, I get 165.8405 plus 11.95465 times 28, which is just over 500 calories. So if there's a burger with 28 grams of fat, I'm going to estimate that the population mean calorie content would be 500.57 calories. And this note here is to remind you that you should multiply before adding. So if you're typing this into your calculator, make sure that you do 11.95465 times 28, and then add the 165. If you do it the other way, you'll get a weird answer that won't really make sense. So what we can do is, once we get this number, 500.57, we could go back to our graph and make sure that it makes sense. And 28 grams of fat, right around 500. All right, so if you made a prediction that didn't make sense, it wouldn't match up with this line here. So that's one thing that we can do. We might also wonder, well, what would the residual be for a burger like the Big Mac that actually does have 28 grams of fat and has 540 calories? So we said that you can calculate the residual by taking the actual y value minus the predicted y value. So in this case, y is calories, so the actual number of calories is 540. We just predicted 500.57 calories, and so the difference between those is 39.43 calories. Basically what we're saying is, if we were to use this line to predict the number of calories in a Big Mac, we would have been off by a little over 39 calories. That's how far away our prediction would have been from reality. All right? So when we're making predictions, there's two different kinds of predictions that we can make. The first kind is called an interpolation, and the second kind is called an extrapolation. And you've probably heard extrapolation before. Interpolation isn't a term we use quite as often, but you might be able to guess that it's kind of the opposite. So an interpolation is when we use our equation, so this estimated line, to predict a response that's based off of x values within the range of other x values that we've already seen. So other x values that we used to calculate this line. Extrapolation is when we use our equation to make predictions that are not within the range of what we've seen before. All right, so for this example, if I look back here at my graph, it looks like the smallest x value I've seen is maybe 18 grams of fat or 19 grams of fat, and the biggest one I've seen is maybe 42 or 43 grams of fat. Okay? So what that means is that if I'm going to make a prediction between 19 and 43 or something like that, any prediction that's for a fat value in that range is an interpolation. I'm making a prediction based on the kinds of things that I've already seen before. So for the Big Mac, 28 grams of fat is within that range. So even if we haven't seen Big Macs before, we've seen, things similar to that. And I'm realizing now that this says no. I will change that in the notes. It should say yes, because this would be an interpolation. 28 is within 19 and 43. So this is a good kind of prediction to make. Now, a bad kind of prediction to make, ones that are not recommended, are predictions well beyond what we've seen before. You might remember in the last set of notes we talked about the Challenger data set, and I think the lowest temperature we had seen was like 12 or 13 degrees Celsius, and we tried to make a prediction for what would happen at 0 degrees. That's actually going to be really hard to do, because we don't know if temperature and damage index would have the same relationship around 0 degrees as it did in the data that we saw. So I'll give you an example here. Did a little research for the set of notes, and the 2/3 pound monster thick burger from Hardee's has 90 grams of fat. So if I were to try to predict the number of calories in the 2/3 pound monster thick burger, I might not be confident that I would make a very good prediction, because the biggest burger in my dataset only had 43 grams of fat. This one has over twice that many, which means that's an extrapolation, and so I don't know if my line is going to do a very good job of making a prediction, since maybe burgers with 90 grams of fat are different in other ways as well. All right? So we want to try to make interpolations and avoid extrapolations. All right? So let's revisit the equation of the line here. We made a prediction for 28 grams of fat. We could do something similar for 29 grams of fat. And the only difference is we're going to plug in 29 instead. And you'll see that we get 512.52 calories. So I had you predict the calories at 28 grams of fat. I had you predict the calories at 29 grams of fat. What we're going to do now is we're going to take this newer prediction minus the prediction that we made before. And if you do that, you get 512.52 minus 500.57. You get 11.95. And this is actually our estimated slope. And so the reason that I'm showing you this is it gives us an insight into what our slope is doing for us. Essentially, the slope is saying that if you increase the grams of fat by 1, if you increase your x value by 1, the slope is how much you think your y value will change, how much our prediction is going to change. So one way to think of the slope is that as we increase the grams of fat by 1, the predicted calorie content increases by 11.95. Now, if this had said negative 11.95, we would say that the predicted calorie content decreases by 11.95. So whatever number we have here, it's how much we think our prediction will change when our x value increases by 1. And we'll revisit this in just a minute on the next page. So what if we made a prediction for a burger with 0 grams of fat? All right, let's look at that. I can just plug 0 into my equation here, and I get 165.8405. And hopefully you can see right away that that's just my intercept here. And so this actually leads us to what it is that our intercept is doing as well. Basically, this is going to be an extrapolation, but you can think of the y-intercept as essentially being our prediction when our x value is 0. And a lot of times this is going to be an extrapolation. All right, so in the next set of videos for this, in part 3, we will just look a little more in depth at how to interpret our intercept, how to interpret our slope, and we'll write out sentences for the burger example to give you sort of a template that you can use going forward when you're interpreting these simple linear regression lines.